Okay, so our next speaker is Sophie Maguire, and Sophie is a third-year PhD student with the Space Environment and Radio Engineering Serene Group at the University of Birmingham. She began her journey into studying space physics during her undergraduate degree at Aberystwyth University, where she studied for an MPhil in physics with planetary and space physics. During her final year, she completed a semester abroad at the University Centre in Svalbard, UNIS. There she studied courses in physics in the upper polar atmosphere and radar diagnostic of space plasmas, and completed fieldwork at the IceCat Svalbard radar and the Shell Hendrickson Observatory KHO. So that led nicely into her PhD work with Serene, where she's been using IceCat radars and other instrumentation to study large-scale structures in the high-latitude ionosphere and their scintillation effect. In addition to Sophie's PhD work, she's also been involved more widely in the community as the Miss Student Representative in 2023 to 2024, and delivering outreach programs to local schools, focusing on the Earth's atmosphere and the effect of space weather. So Sophie's title of her talk is Large-Scale Plasma Structures and Scintillation in the High-Latitude Ionosphere. So I'll hand over Sophie now.
Thank you, Rosie. So yeah, good morning, everyone. As Rosie said, I'm Sophie Maguire, and I'm a third-year PhD student with the Space Environment and Radio Engineering Group at the University of Birmingham. And this morning, I'm going to be presenting my PhD work to date. So we're going to be covering two experiments which look at structuring and scintillation in the high-latitude ionosphere. So jumping straight into it, both of the experiments we're going to be talking about this morning use the IceCat radars. So these are incoherent scatter radars in Scandinavia, and for this experiment, we're going to be using the IceCat Svalbard radars, which we can see in the top here, which is comprised of a 42-meter field-aligned dish and the 32-meter dish. And we also used the UHF radar and the VHF radar down in Tromsø on mainland Norway as well. So these radars have a variety of powers and frequencies, and the thing that we really utilised in this experiment was the different pointing directions. So we used the ESR 42-meter, which is a field-aligned dish, and we also took advantage of the steerability of the UHF and the VHF, using the VHF at a lower elevation and also steering the UHF in azimuth and elevation as well. And from this, then, we were able to get the observed parameters of the ionosphere, of the electron density, the electron and ion temperatures, and the line of sight velocities. So just before we jump into the experiments and we start going through the results, I'll highlight the features that we were looking for in the data sets. So firstly, we have polar cap patches, which are large-scale ionospheric structures found in the F region, and they are defined as density enhancements of at least twice the background density. So if we have a look at the figure on the right, we have an example of it from IceCat data. This is from the ESR 42-meter. And in the top, as a function of altitude and universal time, we have the electron density in the top panel and the electron temperatures in the bottom panel. And the polar cap patches we're looking for are these large red enhanced regions of density that we're seeing in the top panel here. Typically, they're also associated with lower temperatures, which we can see in the bottom panel. And these structures are transported across the polar cap where they enter the auroral oval and they become blobs. So we'll be looking at three key types of blobs. Firstly is the boundary blob, then the auroral blob and subauroral blobs. And these vary in location from the equator to auroral boundary, in the oval and in the ionospheric trough region. But what we're going to be focusing on primarily today is the formation mechanisms. So as we can see, boundary blobs and subauroral blobs are formed from transportation effects. So this is the physical movement of the plasma from the polar cap into the auroral oval. And then auroral blobs are formed by auroral precipitation. So starting off with the first experiment this morning, we have SGRAD. So that's scintillation and plasma density gradients. And essentially what we did in this experiment was we had the configuration set up as followed, with the ESR 42-meter in the north on Svalbard, field aligned. And then on the mainland in the south direction, we had the UHF radar at an elevation of 60 degrees and the VHF radar at an elevation of 30 degrees, with both of those radars pointing northwards towards Svalbard. And essentially the idea here was, if we imagine my pointer is a blob or a patch, once we see these structures move anti-sunward, we will see them first in the ESR, then in the VHF radar, and then in the UHF. And from this configuration, we can track the evolution of those structures. So into the results, we first have the results from the ESR 42-meter dish. And we have in the figure, as a function of altitude and universal time, from top to bottom, we have the electron density, the electron temperatures, the ion temperatures, and the ion drift velocities. And what we can see here is, again, in the electron density, we're seeing these enhanced regions of density, which are our polar cap patches. And the rest of the data set is pretty stable, which this is a pretty typical data set, considering we've got relatively quiet geomagnetic conditions. So we have a KP of 3. So we're not expecting massive disturbances here in the data anyway. But it's in the VHF radar here that things start to get a little bit more interesting. So again, looking in the top panel in the electron density, up in the F region altitudes, we're seeing evidence of polar cap patches and blobs. And in the lower altitudes here below 200 kilometers, we're seeing these slanted density structures, which are indicative of auroral precipitation. There's also some interesting features in the temperatures here. So this enhancement in the electron temperature, some variation in the ion temperature as well. And in comparison to the ESR 42-meter dish, we're now getting some useful information in the ion velocities as well. But what we're actually looking at here, and of particular interest to this experiment, was this patch that we see at approximately 2030 UT. And we see this polar cap patch centered in altitude at about 400 kilometers. And then 15 minutes later, we see it become lower in altitude, which is also lower in latitude, and the density increases. And we believe that the density increases because of the auroral precipitation that we're seeing here below 200 kilometers. Now, for the density to be modulated by the auroral precipitation, we're saying that two things must have happened. Firstly, that the patch that we see here has transported into the auroral oval, and therefore we should be able to track those structures moving through the different radars, so from the ESR to the VHF and the UHF. And secondly, that the auroral precipitation is there to modulate the density, and so we must have crossed the open-closed field line boundary into the auroral oval. So firstly, we'll identify have we moved into the auroral oval, and to do this, we're using the electron temperatures as a proxy for the open-closed field line boundary. So we have the electron densities from IceCat on the left and the temperatures on the right, and we've rescaled this here in latitude. So what we're going to do is take the electron temperatures, we'll take the bit that we're interested in, so this region of high temperatures above about 2000 Kelvin, we'll overlay the two. And then what we're going to do is rescale the electron temperatures. So we're only picking out temperatures above about 2000 Kelvin, and we will overlay this onto the density. And what we can see here is that when we have the patch that's modulated in density, we're firmly within this boundary that we've set. And so from this, we can say that we have crossed the open-closed field line boundary and that we're now in the auroral oval. So the second assumption that we were making was that we were moving with a set velocity, and therefore we would be able to see the patch first in the ESR, then in the VHF, and then in the UHF. So using the velocities from the VHF radar, we estimated a speed of around 400 meters a second. And so from this, we're able to first identify the patch here. Just before 2030 in the ESR radar, we then track the patch forward in time, where we find it here in the VHF, where it's modulated by the auroral precipitation, and we see that later in time at around 2045. And then finally, we're able to track it forward again into the UHF radar, where we find the patch here at 2100 UT approximately. But are all of these things reasonable assumptions? Well, firstly, to check we made a reasonable assumption on the velocity. Again, we measured that using the IceCat VHF radar, so it's a direct observation. We wanted to consolidate this with these SuperDARM radars. So we have three plots here. and each timestamp corresponds to the time at which we see the patch and the blob move in each radar respectively. So the first one, we have the ESR, then the VHF, and then the UHF radar. And from this, you can see that on the day side of the Earth, we have speeds that are measuring between 500 to 750 meters a second. And this is a lot quicker than what we're seeing directly observed with the VHF radar. But if you notice that on the day side of the Earth, we have very little observation, and it's heavily driven by the background model. And that's because some of the SuperDARN radars were not operational during this time window. So while we don't get a direct observation at this time, we are seeing that the SuperDARN results are consistent with what we see with the IceCat VHF. And then we want to look to see if we've crossed into the open-closed field line boundary. And we did this by using the electron temperatures from the VHF as a proxy for that boundary. But we've also had a look at the ampere data that we have. This is the only current plot that we have for this time. And this is the quick look data. And again, in the region with IceCat down here and the ESR up on Svalbard, we are seeing that there is changes in the current density across that region, and roughly the open closed field line boundary is where we'd expect it to be, having a quick look at this data. So we've now found the patch in the ESR, it's moved to the VHF where it's crossed into the open closed field line boundary, into the auroral oval, and it's became a blob. And then we've identified it in the UHF later in time as well. So now what we want to do is say, okay, well, what scintillation effects do we get associated with these structures? So I'm going to quickly run you through the scintillation theory before we jump into that. And essentially, when we're talking about scintillation in this context, what we're saying is we have a uniform ionosphere. And then when we have a signal from a satellite, such as a GNSS satellite, the signal comes down, propagates through the ionosphere where it's refracted, and then we get a received signal on the ground. But this is all theory, and in actuality, the ionosphere looks a little bit something more like this, where it's full of structuring of different scale sizes and different irregularities that change spatially and with time. And so what happens is when we get the signal coming down through the ionosphere, it gets refracted, diffracted, we get interference, and so we get a range of different signals back out, which is then received at the ground. And that fluctuation, the rapid change in the fluctuation of the signal, is what we're referring to as scintillation in this context. So we'll have a look at the amplitude scintillation. And now I appreciate there is a lot going on in this plot, so we'll talk through it step by step. And so essentially on the coloured part of the plot, what we have as a function of altitude and universal time is we have the electron density data that we see on IceCat. So before from the VHF, we have the plot here, the patch here, which is modulated in density, and then there is the auroral precipitation underneath. Now we've taken the amplitude scintillation measurements and we've overplotted those onto the top if they fit two key criteria. The first criteria being that they meet an elevation cutoff of 30 degrees, and the second being that at any point the scintillation measurement is within 50 kilometers of the IceCat beam. So then, assuming an ionospheric pierce point of 120 kilometers, which is roughly where our E region is, we have this amplitude scintillation layout. Again, because of the low elevation of the radar, we're expecting the south of the plot to be at the bottom and the more northern latitudes to be up here. So I've dropped the latitude scale on here as well, just for clarity. And overall, what we're seeing is we're getting a lot of amplitude scintillation. We have a range of different points, but the amplitude scintillation isn't that strong. So we're not really seeing anything above 0.1, which is very weak scintillation at best. We're seeing scintillation associated in times here of in gaps of low density areas of the data. We're also seeing some correlation here and some association with auroral precipitation. But specifically at the point at which our patch becomes a blob and crosses into the boundary and gains density, we are seeing some associated scintillation effects here, even if they're really minor. If we change the ionospheric pierce point to 350 kilometers, we're again seeing the same thing. Amplitude scintillation associated with much lower areas of density. We're seeing some fluctuation in the amplitude scintillation associated with our larger scale structures up here. But at the point where we're seeing the patch turn into a blob again in this pink box, we're not seeing any associated scintillation effects. And so this tells us two key things across these two plots. Firstly, that the scintillation that we are seeing is more closely related to the auroral precipitation as opposed to the large-scale structuring. And secondly, that the auroral precipitation that we are seeing should therefore be soft precipitation. So just to summarize the study before moving on to the next, we therefore have seen boundary blobs be formed by different formation mechanisms. So we're seeing these precipitation effects, but also transportation. And we know that patches can leave the polar cap to become blobs in the auroral oval. And what we've seen here is the polar cap patch exiting the polar cap, where it becomes then a boundary blob that is then further structured by the precipitation in that region. At this time, we see amplitude scintillation associated with the auroral precipitation, but not necessarily with the large-scale structuring. And to be able to make any more useful conclusions on this, we need to understand much more about the scale sizes of the structuring that we're seeing that causes the scintillation. Which brings us nicely onto the next study of the PhD, which was SIPS. So SIPS, Scales of Ionospheric Plasma Structuring, was an experiment of my own design, which used the IceCat Svalbard radars again. And from this, we were able to look at large-scale plasma structures that you get in the high-latitude ionosphere. The presence of instability mechanisms in this region then lead to smaller scale irregularities, which you can measure with radio telescopes. For example, we have Kyra here. And then this leads to GNSS scintillation. So the aim of this was to look across as many scale sizes as possible, and we needed a range of instrumentation to do that. So having a look on the field of view on the right-hand side here, we first of all have the IceCat radars. Again, using the ESR42, the UHF and the VHF radars, we're able to look at large-scale structures on the scales of hundreds of kilometers in size. Then we have Kyra, so the Kilpisjärvi Atmospheric Imaging Receiver Array, which is a radio telescope located down here. And from this, we were able to look at structures on the orders of kilometers in scale sizes. We also had the swarm satellites pass over during these regions of time. And we were able to then use the Swiss model from INGV, which allows us to take measurements of the electron density and map those down into a spectrum of irregularities at the F-layer peak. And finally, then we have GNSS receivers, which is going to give us information on the orders of hundreds of meters and really let us get down to see what's causing the scintillation in the high latitude ionosphere here. So having a look at the data from this, we're going to present a few of the preliminary plots, and we're going to compare 2 days of data. So a more active day and a quieter day. On the more active day, we have a KP of 3, and on the quieter day, we have a KP of 0. And I'd just like to preface this by saying I'm not by any means saying that a KP of 3 is an active condition. We're not expecting any huge geomagnetic storms or anything like that, but just that it is more active relative to the quiet day. So starting with the ESR data, again, we have the densities and the temperatures. And you can see that on the more active day, we've got much higher densities and structuring in the electron density. We've got electron temperatures as well that are pretty high associated with this. And in comparison, in the quieter day, we're seeing a lot less high density structuring, and we're seeing low temperatures as well. The UHF for this particular experiment was aligned such that it intercepted with the IPP of Kyra. So we're getting co-located measurements. And we can see here that, again, a similar story, enhancements in the electron density on the active day with some variation in the electron temperatures. And there's not really anything happening of much significance in the electron density data or the temperatures for the quieter day. The VHF observed vertically in this instance of this experiment. And again, same story, much higher electron densities on a more active day than on the quieter day, and the same in the temperatures as well. So then moving on to Kyra, which is going to give us our smaller scale structures. So on the orders of kilometer sizes. We're going to use Cassiopeia A as our radio source here. And essentially what we're looking at in the plot is we have as a function of frequency and universal time, We have the coloured data, which gives us the relative change in the signal intensity that we're receiving. So we can see here that in the more active day, we're seeing much more structure in the higher frequency bands, which is presenting vertically. We're also seeing quite a lot of structure in the lower bands as well. But where it starts to get interesting is actually over on the quieter day. So firstly, we can ignore this big red blob in the middle because that's radio frequency interference. And what we're actually interested in is these smaller, more dispersive features that we're seeing down in the lower frequency bands. And it's these features that we think should be correlating to larger scale structures and other structuring that we're seeing in the ionosphere. So finally, we'll take a quick look at the GNSS scintillation before we conclude. And what we're seeing here is, again, remember, we're looking at structures on the scale sizes of hundreds of meters now. We have a comparison between two different timestamps for the quiet and the active day, and we're looking specifically at the amplitude scintillation and the total electron content. So over on the more active day, we also have the all-sky imagery overplotted on the top, giving us an idea of some of the intensities here. And what we're seeing is some of these little yellow blobs scattered around on the plot, which tells us we're seeing scintillation of between 0.2 and 0.4. We're also seeing loss of lock of the satellites on the signal in some cases as well. And we're also seeing a fair bit of variation in the total electron content here, up to about 25 tech units in some places. Whereas again, as has been the case for all the other data sets as well, we're seeing much less activity in the quieter day data. We're seeing some instances of amplitude scintillation, but we're not seeing any loss of lock as we are on the more active day. And the stark difference here is in the total electron content, where we're not seeing anything really above 10 tech units. So in summary, I have presented two studies here this morning, SGRAD and SIPS, which have been the studies and the work that I've done today on the PhD. SGRAD has observed multiple blob formation mechanisms acting simultaneously on the same plasma at the same time. And we believe that these are some of the first direct observations of this. And this work is currently in preparation, so is going through the final stages of being written up to go out with co-authors and enter the review process towards the end of this month. We then followed on from SGRAD with the unanswered questions we still had, and we designed SIPS. This went in as an IceCat time proposal and was awarded 72 hours of experimental time, which all ran in the winter of 2024. And then from this, we've presented some of the preliminary results this morning, where we're exploring the ionosphere across multiple scale sizes. And the next steps for this work is to be able to track these features across data sets. So can we take the large scale structures that we see in the ESR and the VHF, for example, can we map those down to some of the dispersive features that we're seeing in the data sets in Cairo? And do we get associated scintillation effects with this? So thank you very much for your attention this morning, and I'd like to welcome any questions.